Namaste, students, and welcome. Today we are going to explore two very important and actually very interesting topics. First, we'll look at the force on a wire that is carrying current inside a magnetic field. Then we will see how the electrical systems in our own homes are designed to keep us safe.
All right, let's begin. We will start with a little revision to warm up our brains. Now, in the previous chapters, we learned that a current-carrying wire creates its own magnetic field. It behaves like a magnet. So we know that electricity and magnetism are linked. This leads to a very important question. What happens when we take that current-carrying wire and place it inside another external magnetic field? To answer our question, we'll look at a simple but very important experiment. You can find this in your textbook as Activity 12.7. It's often called the kicking wire experiment, and you will soon understand why it has such a funny name.
Let's observe this setup very carefully. We have a small aluminum rod, which we can call AB, and it is suspended so that it can move freely. Now look where it is placed, right between the north and south poles of a strong horseshoe magnet. This is important. The magnetic field is directed vertically upwards, going from the north pole at the bottom to the south pole at the top. Now watch what happens. As soon as we connect the battery, and a current starts to flow through the rod, it moves. It gets a little kick and is displaced towards the left. This is our first big clue. It clearly shows that some kind of force is acting on the rod when it carries a current inside the magnetic field. Now let's try something. What happens if we reverse the battery terminals? The current will now flow in the opposite direction. And look, the displacement also reverses. The rod now gets kicked towards the right. This is a very, very important observation, students.
So, what is the conclusion from our experiment? It's simple. First, a force is exerted on a current-carrying conductor when it's placed in a magnetic field. And second, the direction of this force depends on two things: the direction of the current and the direction of the magnetic field. Remember this: if you change either one, the direction of the force also changes. So, we know this force exists, but is there a way to predict its direction without doing the experiment every single time? Yes, there is. For this, we use a very simple and useful trick called Fleming's left-hand rule.
Okay, everyone, I want you to please do this with me right now. Hold up your left hand. Now, stretch out your thumb, your forefinger, and your middle finger so that they are all at right angles, that is, perpendicular to each other. Try to make it look just like the hand you see on the screen.
Now let's give each finger a job. Your forefinger points in the direction of the magnetic field. Your middle finger, which is in the center, points in the direction of the current. And if you align these two correctly, your thumb will point in the direction of the force or the motion. Let's repeat that slowly so it sticks in your mind. Forefinger is for field, center finger for current, and the thumb shows the force.
Okay, let's try to solve a problem together using our new rule. Imagine an electron enters a magnetic field. The crosses on the screen mean the field is directed into the page or into your screen. So, take your left hand and point your forefinger for field straight into your screen. Now, the electron is moving from left to right. The question is, what is the direction of the current? I want you to think carefully about this.
This is a very important point, and it is a common trick in exams, so listen carefully. The direction of conventional current is always taken as opposite to the direction of motion of electrons. So, if the electron is moving to the right, the current is actually flowing to the left. Now keep your forefinger pointing into the screen and point your middle finger for current to the left. What do you see? Your thumb is pointing downwards. That is the direction of the force. Okay, one more. What if a proton moved from bottom to top with the field still into the page? A proton's charge is positive, so the current is in the same direction. Forefinger in, middle finger up, your thumb points left. The force is to the left.
Now, this principle is not just some theory in a textbook. It is the fundamental concept behind every electric motor that is used all around us, in our fans, washing machines, mixers, computers, so many devices. It is this very force that we just learned about that makes an electric motor rotate. Now that we understand the powerful force that electricity can create, let's shift to a very practical topic. How is this powerful electricity managed safely in our own homes? We will now connect the physics we just learned to everyday safety.
In our domestic wiring, you will typically find three types of wires. This table summarizes everything you need to remember. First, the live wire, which usually has red insulation, is at a high potential of 220 volts. This is the dangerous one. The neutral wire with black insulation is at 0 potential. And the third is the earth wire with green insulation, which is a very important safety wire. Please take a moment to remember these colors and their functions. It is very important.
So, why do we have this earth wire? The crucial point is that earthing is a safety measure. For appliances that have a metal body, like a refrigerator or an electric iron, the earth wire is connected directly to this metallic body. Now imagine if, due to some fault, the live wire accidentally touches the metal body. The earth wire provides a safe, low-resistance path for this dangerous current to flow directly into the ground instead of through you. This is what prevents a severe electric shock.
All right, let's consider another safety problem. Sometimes the current flowing in a circuit can suddenly increase to very high unsafe values. What do you think would happen to our expensive appliances, like a TV or a computer, if this happens? What is there to protect the circuit?
There are two common reasons for such a dangerously high current. The first is a short circuit. This can happen when the insulation on the live and neutral wires gets damaged and they touch each other directly. This causes a massive, sudden increase in current. The second reason is overloading. This is what happens when you connect too many heavy appliances to a single socket, like on an extension board. The circuit is then forced to draw more current than it can safely handle.
And this is where the simple but very effective electric fuse comes in. When a very high current flows, the thin wire inside the fuse heats up very quickly due to the Joule heating effect. This wire is designed to have a low melting point, so it quickly melts and breaks the circuit. The flow of current stops completely, and our appliances are protected. So you see, the fuse actually sacrifices itself to save the rest of the circuit.
Before we end our lesson, let us calmly recap the key points that you must prepare properly for your examinations. This is your exam checklist.
Please make a note of this checklist. For your exams, it is very important that you can explain each of these concepts clearly. You must also be able to draw the necessary diagrams, especially for the kicking wire experiment and for Fleming's left-hand rule.
And I will leave you with a final question to think about. Every time you switch on a fan or use a computer or even just turn on a light, an entire system of physics principles and safety features is working silently to help and protect you. Physics is all around us, often in ways we don't even notice. So, my question to you is, what other invisible science is protecting you in your daily life? Thank you, and study well.